So this is a short talk through for Workshop 7, where we're going to look at the calculation and analysis of anomalies relative to a seasonal cycle in a long-term series of temperature data. The data were downloaded from the Met Office from the link provided in the instructions, where there are various historic recording stations dotted around the UK. The end result of this workshop will be the plot shown here, where we have temperature anomaly. So this is the monthly temperature with the seasonal variation subtracted from it. Over a long time period, from the end of the 19th century all the way through to the present day at a site in the Outer Hebrides off Scotland at Stornoway. And the blue line indicates the temperature anomaly. The red line is a smoothed version of that to clarify the overall trend. And then the green line is a linear fit to that data to show a rate of change with time. The follow-up to this is to apply the processing that we'll cover to a second data set from Lowestoft in the southeast of the UK. So I've got MATLAB started. I'm just going to double check my path, and I'm going to remove any extra things over above the default MATLAB paths. I'm then going to change to my folder, which is the Workshop 7 folder on my desktop. And the first thing I'll do is to create a new folder called mfiles to store the scripts and functions I create during the session. And I'm then going to add that folder to the path before then changing into the data folder. So in the data folder, I've got these two data files, one called Stornoway and one called Lowestoft. So we'll figure out how to load them by first having a look at them. They're text files, so I can open them as text. And here we can see that we've got some header information before we get onto the numerical data. Unfortunately, the numerical data isn't that easy to deal with because it's got these minus symbols in where there's missing data. And if we have a look at the other data file, the Lowestoft data, you can actually see it's got a slightly different number of header lines, and it's also got some estimated data, which has got a star at the end of it. And so we're going to have to deal with these issues in with our processing as how we load up the data. So to load the Stornoway data, I'm going to start a new function. It's going to give me some data back, and I'm going to call it load data as ever, and I'm going to give it the file name of the file. I'll then write a comment, and I will then just save this into my mfiles folder, and it will be called load data. So first thing I'll do is open the file and assign the file identifier to a variable I'll call FID. I can call it anything, but I'm calling it FID. So F open and then file name. So that opens the file. And then if we have a look at the format, we need to read this line by line until we get to the data. But we don't know how many lines we're going to read. But we do know that 2 lines before the data starts, you get a line with this header information on it. So if we look for the characters YYYY, then we know that 2 lines later we get the first line of data. So I'm going to start reading in the data line by line. So I'll fill a temporary variable called tline equals f get line, f get l, and then fid. So that reads the first line. And then I'm going to go into a while loop, and it's basically just going to check that I haven't reached the end of the file while is_char tline, and then I'm going to check to see what the contents of the line are, and if they contain that series of characters y, then I'll exit from this loop and then read 2 more lines of data before I get to the first line of data. So I'll go if, and then I'll say strFind, which is a MATLAB function which finds a pattern within a string. The string is going to be tline, which is the line I've just read, and then the pattern is y. Now, if strFind actually finds this pattern in this string, then it returns a number saying whereabouts in the string the number, the pattern actually is, at which point this would be valid, at which point I want to exit the loop. And to exit a loop, I say break. But if I don't find it, then it returns an empty variable, at which point the if statement becomes false. And so I would then read in the next line. So I'd say tline equals f get line fid. And so this while loop will keep going round until it finds that y, or until it reaches the end of the file. It's then going to read 2 more lines, and then I know that I'm at my first line of data. I should have also, right down at the bottom here, said that I'm going to close the file just to tidy up once I've exited the function. So now we've reached the first line of data. If I copy that across into here, then I can see what format I'm working with. So the format is the year, the month, and then 1, 2, 3, 4, 5 numbers, which could also be strings if they've got missing data, or they could be a string if they've got a star at the end of them. So I'm going to use the text scan. So I'm going to say TMP for temporary output equals text scan to break this line of text into chunks. And I'm going to give it the line of text, and then I'm going to tell it the format. So I'm going to say %f, and that %f means a floating point number. So that reads in the year and then the month as numbers, and they're always numbers. Now I use %f to give a floating point number because I'm shortly going to use a date num, and that needs a floating point number as an input rather than an integer. I could load these in as integers, which would be %d, but then I would have to convert them into floating points before I use the date num function. So %f gets round that. I then read in 5 strings, which will then load in these numbers or the dashes depending on what they're actually going to do. Next thing I can do is I can create the output data.datetime equals, and we're going to have the year and the month and then the first of the month. So I'll say date num, and then it's tmp1, tmp2, 1. Now I use the curly brackets here, here and here because that accesses the first and the second cells of this cell array, the text scan output. So text scan outputs a mixture of numbers and strings, and so these are cell arrays, and to get at the elements of a cell array I use the curly braces, and we'll see curly braces in use later on. So this gives me the date, time, and then I'm going to read the temperatures. Now historically, these temperatures, these are monthly maximum and minimum temperatures, were recorded using mercury thermometers, and then the numbers were noted down. And so we don't have a mean temperature. So we're going to fudge this for this particular exercise and calculate a mean of these two numbers. So we'll add them together and divide by 2. And that will be the temperature which we're then going to be using. Obviously, this is not a particularly accurate measure of the monthly mean that we're using. It's just the midway between the maximum and the minimum monthly data. So I'm going to create a temporary variable for the temperature. I'll call it T equals, and then we're going to convert the strings that we've extracted, and then we'll average them. So we'll do the averaging. So we're going to be doing a sum, and we're dividing by 2, and we're summing up str to num. So we're converting the strings to numbers, str to num, and then we are doing tmp and then curly brackets 3 and 1 and curly brackets 4 and 1. Now this second curly brackets 1 basically takes the first string out of a potential list of strings that would be in the third cell of this cell array. And putting this here is similar to, in previous workshops, we've used the function cell to mat. So we could have said cell to mat tmp3, and then we could have said string to num of that cell to mat. But this is basically a shorthand to that. It says take the first string out of this cell and then convert it into a number, and then add it to the first string out of this cell, convert that to a number, and then divide by 2. Now, if we have the characters minus, 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 then the str to num returns an empty variable, and that means that t will be empty. So we then want to do a quality control on it. So we want to say if is empty t, then we want data.t equals not a number, else data.t equals t. Okay, so we'll save this, and then what we're going to do is go to our command window. I'm then going to run it and test it by typing load data stored away data.txt. And I've got a bug in my code, so I go to, let's just have a quick look at the bug. It says unbalanced or unexpected parenthesis or bracket. So it means I've got a problem probably with my brackets on line 20. If I click on that, then I look at line 20. Now you can see here that I have got some slightly unbalanced brackets. So str to num, and then tmp3, 1, and then this bracket here shouldn't be there. And then str to num, and then I should have said tmp41, and there we go. So I think that's going to work. So we'll do load data, and then we've got the date time loading in and the temperature, which is the average of the two. So again, when bugs happen, and you can see bugs do happen, you need to read what the warning says. It might not be exactly what the error message says. In this case, I've missed out the word TMP and I got a bracket in the wrong place. Okay, so we've got a way of loading in one line of data. What we need to do now is to put this scanning into a loop, and we're going to use a while loop. So is char t line. So again, check for the end of the file. I'm going to put an n down here, and then I'm going to indent this to make it more readable. I then need to, at the end of this loop, read in the next line of data, and I also need a counter. So I'll say Q, which is my counter, equals 1, and then I will say data.datetime Q. I'll then say data.t Q, data.t Q, and then I'll say Q equals Q plus 1. So this now should load in all my data. So if I then say data equals load data, then I've got 1720 data points, and I can quickly plot them up. So I can say data.datetime, data.t, and then I can say date tick, and you can see that we've got the time period from on this axis 1873 to 2020, and if we zoom in, then we can actually see the seasonal cycle that is quite large. So you can see we've got a seasonal cycle which is from about 4 degrees up to about 13 degrees, and that hides what may be quite a small trend or change in the temperature over this period. So the next thing we're going to do is to remove the seasonal cycle. So we'll create an average seasonal cycle, and then we will remove that from each month of data, and then what we'll be left with is the anomaly, which will be much smaller with that seasonal cycle removed, so we can more clearly see a long-term trend. Now, to find all the data from any particular month, say all the data from January, and then create an average of it, and then all the data from February and create an average of that, to create and so on with the other months to create an average seasonal cycle, we're going to take advantage of there being this month number in our import data. So we can basically find all the data where this month is equal to 1, and that will be all the data from January, and then we'll take an average of that. So here, where I create the date time, I'm going to create an extra variable called data.m, and Q, which is our counter, equals tmp2. So that takes the second number and is our month. Okay, and we may as well do the averaging within this load data function. So down at the bottom, after my while loop, I'm then going to create another loop where I'm going to step through each month in turn and create the average of all the data from that month, and then I will take that average away from all the data that was recorded in that month. So I'm going to create a loop for each of the 12 months, so I can use a for loop because I know how many steps I'm going to do. So I'll say 1 to 12, and I'll use a counter called big M for each of the months. And for each month that I go around, I'm going to say create me the monthly average. So I'll say data.month average big M equals, and then I want to take the mean or the average of all the data that was recorded in, say, January. Now, what I've got to do is make sure that I can cope with not a numbers. So some of my data are not a numbers, so I've actually got to use the function nan mean. And this is in the statistics toolbox, so if you've got MATLAB installed on your laptop, make sure that you've got this nan mean function available to you. And I'm then going to take the nan mean of the data.t, where data.m is equal to big M. So that basically, this is a shorthand way of doing a find, so it's basically saying where the month is equal to the month in question, then select all of that temperature data and take the mean of it. I'll just make sure I've got enough closing brackets, so that's that closed, and then it's the man mean closed, and we'll put a semicolon there. And then once I've created that monthly average, I'm going to subtract that from all of this temperature data. So I'll then say data.t of data.m from the month that we're looking at equals data.t data.m equals big M minus data.month average M. Now, instead of calling this T, I'm actually going to say T anom. So this will be the temperature anomaly, so I can do that as a separate plot. Okay, so if I save that and then run it, when I run this, data equals load data, stored away data, what I now have is this M output, which is a list of the month of each data. And I've got the month average, 12 data points, and I've also got the temperature anomaly data. So I can do a quick check of what the seasonal cycle looks like, the average seasonal cycle. So I can do plot, and then I can do data dot month average, and this shows as a function of month through the year, this shows the average seasonal cycle in the temperature. So you can see it goes from about 4 degrees up to about 13 degrees. And then if I do a plot where I'm now going to plot the date time and the T anomaly, then what we've calculated here is the temperature at each month with that mean seasonal cycle removed from it. So I can now do date tick, and I can add a Y label, which is temperature anomaly in degrees centigrade. And this is the year, and then I can put a title on Stornoway. So we've got the basis of the plot that we're working towards. What we can do next is we can create a smoothed output to overlay on top of that, so we can see the overall trend in the data. Now, the problem is that we've still got some of these not a numbers in here. So instead of having these not a numbers, which will create problems when we come to smooth the data or we try and fit a line through that data, is we're going to remove those not a numbers and replace them with an interpolated value. Now, an interpolation is where you basically draw a straight line across missing data points. So to interpolate the data, we'll adapt our loading function. So we will first find the and remove the not a numbers from the date time variable. We'll then find and remove the not a numbers from the temperature or the anomaly output, and then we'll interpolate across those. So I'm going to create a temporary date time variable, and I'll say that's data.datetime, and I'm going to find only the data that isn't a not a number. So I'll say give me data.datetime isn't, so that's a tilde, isn't is not a number of data.tanom. So that basically says look in tanom and tell me which of these lines are not numbers, and then return those and set them to this temporary variable. And then I'll say temporary t equals data.tanom, and then tilde is nan data.tanom. Okay, so I've now got two temporary variables which have had the not numbers removed, and then I'm going to just rewrite my tanom data. So I'll say data.tanom equals interp1, which is the MATLAB function to do an interpolation, and I give it the known x values, which are tmpd, known y values, which are tmpt. So these have had the not numbers removed, and then I'll give it the complete data.date time matrix, so that at each of these complete date times I will have then an interpolated t anomaly. Okay, so I'll save that, and then I will rerun my data equals load data store away, and I will redo my plot, and I will put a title on it, I'll put a y label, and I'll put date ticks. So here you can actually see there was a little gap here previously, but now we've interpolated across that with a small straight line. Now you've got to be careful with interpolations. Interpolation is basically making up values where there are no known values, and so it can be a risky thing to do, particularly if an extreme event has been cut out and you're then replacing that with values that are not extreme, and so you can bias the interpretation of your output. However, interpolation can be very important to do, particularly if you're then going to do some sort of spectral analysis which relies on regularly spaced data with no missing data points within it. So if you were to do a spectrum of this data series, you would have had to have done this interpolation step first. So now that we've got interpolated data, so we've got no missing values, then we can calculate a smooth version of the data set. So I can say data.tanom and then smooth equals, I'm going to use the MATLAB function filt. Basically this does a symmetrical filtering, you can read up the help on this, and it runs a filter first in one direction over the data, then back the way, so that you end up with a symmetrical filtering of the data. And you give it two numbers which basically determine the coefficients that you're using for the weighting average. And we're going to do a moving average, a filter which is 12 months wide. So I'm going to say 1s, 12,1 divided by 12. So that gives me 12 equally weighted averaging values, and then I do comma 1, which is the numerator that I'm going to be using, and then I give it the data that I'm going to filter, which is data.tanom. So this filtering then allows me to say hold on, and then I can plot. Now instead of tanom, I do tanom smooth, and I will do a red line, and I'll say line width 2. So we then have a nice clear trace which shows the smooth version of this noisy anomaly signature. So you can see at times we've got an overall increase over time, and at times we've got a faster increase, and at times we've got a slower rate of increase. Okay, the final thing we need to do is to calculate what the mean rate of increase in temperature is over this time period. I'm going to do a poly fit for that. So if you remember, polyfit generates some coefficients. So polyfit fits a polynomial, we used it last session, and you give it the x data, so that's data.date time, the y data, which is data.t anomaly, and then you tell it the type of fit you want, and we're doing a straight line fit, so we put a number 1 in there. And this generates two coefficients. First is the gradient, or the rate of change, and the second is the y-axis intercept. So if we say coef 1, this is the rate of change, or the increase in temperature per day. So this is in degrees centigrade per day, which is 2.3 times 10 to the minus 5 degrees centigrade per day. If we multiply that by 365.25, that then gives us the increase in temperature per year, and then we multiply that by 100, and that gives us an increase in temperature for our data set of 0.84 degrees per century as the increase in temperature due to global warming at this site. Now, if we want to put that trend line on the graph, I create another set of data, and I'll call it data.t anom fit equals, and I use polyval function. I give it the coefficients, and then I give it the x values, which is data.date time. And then I can do another plot, and in this case I'm plotting t anom fit. I'll do a green line, and there we go. We've got our final figure with the straight line showing the overall trend, the red line showing the running average with a 12-month running average of the temperature anomaly data at Stornoway for the period 1870 through to the present day. Now, the follow-up exercise for this workshop is to repeat this for the Lowestoft data. Now, if you step through all of the steps that we've just done, you're going to encounter a problem with this Stornoway data file, with the Lowestoft data file. And if you scroll down to the end of it, you'll actually see that it's to do with these asterisk star characters that are on the end of the numbers. When these are loaded in, this won't be recognized as a number because it's got a star on the end of it, at which point it will then be set to an empty value by the string to num function, and that will then mean that these data points are replaced by not a numbers. And then when you try and interpolate these final values, you can't interpolate beyond the end of a known point. That's an extrapolation. And so what you're left with is a whole series of not numbers, which you then can't fit your data to. So we basically need to adapt our load data function so that it can cope with finding these asterisk characters and then removing them. So we can do that if we go back to the load data function just before we do this t calculation. So what we want to do here is, I'm just writing a little comment to indicate, so after we've extracted the m, we're going to find and remove the stars from the numbers. Okay, now we can do that quite simply by saying, well, if there is a star on the last character of this string that we've just read in, so if there is a star, then remove it, and then carry on with your calculation. And if there isn't a star, then you just carry on with your calculation. And we can do that by saying if, and then we want to say tmp, which is the variable that we read in, and we want to say 3 for that first number, and then we want to say 1, which pulls the first string out of this third cell, and then we want to say in round brackets end is equivalent to, so that's double equals, and then star. So that says if that the last character, the end character in the string, the first string of the third cell is equal to a star, that means that we want to say TMP 3, 1. So we basically want to take that first string in the third cell and replace it with TMP 3, 1, the first string in that third cell, and we'll take the characters 1 to end -1. So that's basically taking all but the last character and assigning it to the value of the string, which will then be converted into a number at this later point. Okay, and then we can copy and paste that and do the same for the fourth string that we've imported. So this was the maximum value, this is the minimum value. Again, we're looking for this star character, and if we save that, and then if we clear all, and then I'm going to do a load data, and then I'm just going to do a quick test of this. So I've loaded the data, and then if I say ans.t nom, you can see that we've got numbers all the way through to the end. I can then repeat the plotting and the calculation of the rate of sea level rise using this data.